Okay, so today's video is going to be a short little review on waves, light, and optics. And I'm going to start actually off by recommending to take a look at the section on single and double slit diffraction in your review book. There's an excellent section. It does a nice job, and I could certainly address any sort of questions that you might have. So let's first start talking about the index of refraction, N. N is defined as the ratio of the speed of light in a vacuum to the speed of light in the material. And the thing that's important about this is I could do a little bit of combining of equations, since the velocity of a wave is equal to F times lambda, and I can then rearrange this and solve this for lambda. So I'm going to get lambda is equal to C over N times F. Now, what is really important is that since the frequency of a wave does not change when it enters a new material, that this C over F for a given wave going from one barrier to another, so this ratio right here, is going to stay the same. So what I could say is that that's just the wavelength in a vacuum divided by this index of refraction. So what I develop here is actually a very useful equation for what we're going to be chatting about in just a moment. Is that the the wavelength of a wave in some material n is the wavelength of that wave divided by the index of refraction. Now, this is not a relationship that's in your reference tables, but it is a very useful one for you to know off the top of your head. So what we're going to be talking about is what's referred to as thin film interference. So you can imagine that there's this 3 layers of different liquids, and we have an N1, we have an N2, and an N3, and we have some light that's coming in, and I'm going to draw it at some slight angle just to emphasize a point, but it could be really anything as long as the angle's not too extreme. This is okay. So what I know is that the wave is going to be partially reflected, partially transmitted, and then it's going to hit the second barrier, and it's going to be partially transmitted and partially reflected. And when this comes back out, it's going to bend at the same angle. And so the question is, if your eye is over here and you're viewing this, what do you see? Do you see bright spots? Do you see dark spots? Are they constructively, destructively interfering? Now, what I want to talk about is the relationship between the thickness, give that as T, of that middle layer there. Because it's really all about the middle layer in order to figure out whether they are constructively or destructively interfering. So what we know is that if the wave comes through this N2, this second material, and it travels one full wavelength, then when it exits the other side, then it's going to constructively interfere. This wave and this wave are going to constructively interfere. So I'm going to see this as a bright spot. So what we can say, since this wave that traveled through here, it traveled through 2 times the thickness, that if 2 times the thickness is equal to some number times the wavelength, then it's going to have constructive interference. So if my m is a whole number, 1, 2, 3, 4, 5, etc., then I'm going to get constructive interference. Now, what's really important that we notice is that that's not the wavelength in N1. This is the wavelength in that second material. So I'm going to put a wavelength in 2. I'm going to erase that a little bit. So the wavelength in 2. So this is going to be equal to m times the lambda in air divided by the n. So I'm substituting in this equation that we just developed right here in for my lambda 2. Now, what I did not talk about is what happens if there's any phase shifts. So what we know is that when light encounters a boundary, when it reflects off of that boundary, and actually this is true for any wave, if N1 and N2, if N2 is greater than N1, then it's going to be shifted 180 degrees or pi out of phase. And if N1 is greater than N2, then there's going to be no shift. There's going to be a soft reflection. So what we can see is that if if we're looking at the boundary, if n1 is greater than n2, which is greater than n3, then there's no phase shifts, no phase change. So the above equation holds true. But also, just as important, that if n1 is less than n2 and it's less than n3, then there's actually two phase shifts. So each one is getting shifted by 180 degrees. And I say each one, the original reflection and the second wave reflection. And if they're both shifted by the same amount, once again, that above equation holds true. But then what happens if there's one phase shift? So if there's one phase shift, the only difference to this above this equation is that we have 2 times the thickness equals m lambda. But for constructive interference, so m will be equal to 1/2, 3/2, 5/2 for constructive interference. So notice that's the opposite from before. And so this is constructive. I'll just leave it, I don't have room. And then destructive is when m is equal to 1, 2, 3. So this is a shift from if there's 0 phase shifts or there's 2 phase shifts. So just be mindful of that. All right, next up is talking about mirrors and lenses. So we'll first talk about mirrors, but then we'll generalize with some key points for both of them. So let's say we have our principal axis. So there's our principal axis, and we're first dealing with a concave mirror. And we have our focal point, and we have our center of curvature, which is also the radius of that mirror. And let's say I have an object that's beyond C. So we have 2 principal rays. We have the principal ray that is going parallel to the principal axis, so starting at the top of the arrow, hitting the mirror, and then reflecting through the focal point. And then we have the other one that goes from the top of the arrow through the focal point, hitting the mirror, and then bouncing back parallel to the principal axis. And that would be the location of the tip of my object. Now, we have a relationship that 1 over f is equal to 1 over si plus 1 over so, where si and so is the distance to the image and the object respectively. And so there's a couple other things that we can take from this. The magnification is equal to hi over ho. That's the height of the image divided by the height of the object, which is equal to the negative of the distance to the image divided by the distance of the object. Now your AP reference tables talks about the absolute value of all this. Okay, but that negative actually is in there, and it's pretty important because it allows you to know whether or not it is inverted. So if it is inverted, and this is true for lenses as well, if it's inverted, then the magnification is negative. So if the magnification is negative, then we know that it inverts. Also, if it inverts, we also know that it is real. Okay? And then we can obviously say the opposite is true. If it's upright, then it is virtual. And the other thing that's important about a diverging and converging lenses and mirrors is that a diverging lens, so if you have a diverging mirror or lens, so mirror or lens, it cannot produce real images. And if you play around with the lens, the ray tracings, you will see that all of your images are going to be upright. And the last thing that I want to just talk about is the focal point. If you have a diverging mirror, so this is kind of piggyback off this, the focal point is negative. And we can kind of see that is if you have a diverging mirror, and here is your object. You have a focal point here, you have a focal point there. Okay, the light is going to go parallel, but since it diverges, it's not going to go through that focal point. Okay, it is going to reflect off, and it's going to reflect off as if it originates, and I can't draw a dotted line here very well. It's going to originate from that focal point. So the light is really going to take a path that looks like so. And then likewise, the second principal ray would be as if it is going towards that focal point, so towards that focal point, and then reflects parallel. And in this case, you'd have to backtrace, so we see that our image would be somewhere right along there. Notice it's upright, notice it's smaller, and all that good stuff. Okay, so that's all for now. If you have any questions about waves, light, or optics, please let me know. All right, have a good night. Bye-bye.